Welcome to part 6 and 7 of your Prove It notes. We're going to start here with part 6. We're going to derive all of our double angle formulas. And what you're going to see is that these double angle formulas actually follow really nicely from our angle addition formulas. So we're going to start with expressing the sine of 2 theta. So notice it's just double an angle. I'm going to break that up into the sum of theta plus theta. So now I can apply my angle addition rules. So this is sine, cosine, cosine, sine. So longhand here, I'd write this out as sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. And if I simplify here, I end up with 2 sine theta cosine theta. So I now have a new identity. The sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So I'm going to box this. Let's do that in red. And this becomes, let's see, how many identities have we done so far? I think this should be our 21st identity now. Now let's do the same thing for the cosine of 2 theta. So for the cosine of 2 theta, I'm going to change this into the sum of theta plus theta. And, whoops, not sine, cosine of theta plus theta. And this is going to be cosine, cosine, sine, sine. So we change this to cosine of theta times the cosine of theta minus the sine of theta times the sine of theta. And if we simplify here, we end up with cosine squared theta minus sine squared theta, which leads us to a new identity. The cosine of 2 theta is equal to cosine squared theta minus sine squared theta. This makes our 22nd identity so far. So far these are pretty easy, and they follow, like I said, real nicely by using our angle addition formulas. Now our next identity is just going to be equivalent to our the 22nd identity here. Okay, we're going to manipulate this and express the cosine of 2 theta a couple different ways. So let's start with cosine of 2 theta equals, and I'm going to rewrite cosine squared theta minus sine squared theta. Now we already know that cosine squared theta is the same as 1 minus sine squared theta. So this is 1 minus sine squared theta. So I'm making the substitution in here for cosine squared theta minus sine squared theta. So this is equivalent to 1 minus 2 sine squared theta. So this is a new identity. I have the cosine of 2 theta is equal to 1 minus 2 sine squared theta. So this is helpful if we want to get everything in terms of just sine squared. So here is a new equivalent identity, identity 23. Now alternatively, I can make another appropriate substitution here by saying, let's start again with cosine 2 theta equals cosine squared theta minus sine squared theta. And here, I will substitute in 1 minus cosine squared here. So I have cosine squared theta minus 1 minus cosine squared theta, which ends up giving me 2 cosine squared theta, because this, I just distribute that negative here, so 2 cosine squared theta minus 1. So this is another unique identity. Well, it's just really a, oops. It's equivalent to our first identity here, just written in a different form, but we have cosine 2 theta is equal to 2 cosine squared theta minus 1. And that makes our 24th identity. Alright, next up we have the tangent of 2 theta, so I apologize, but we're going to have to move this over here. We kind of ran out of room, or I ran out of room, hopefully you didn't, but let's express the tangent of 2 theta. So we have tangent of 2 theta is equal to the tangent of theta plus theta. Now we'll use our addition formulas here. We'll use the tangent addition formula, and that states that we have the tangent of theta plus the tangent of theta over 1 minus the tangent of theta times tangent of theta. So again, I'm just using our angle addition rules that we learned in part 5. Okay, so from here I can simplify. That gives me 2 tangent theta over 1 minus tan squared theta. So here is a new identity. The tangent of 2 theta is equal to 2 tangent theta over 1 minus tan squared theta. And this gives me my, I think I ran out of track of the number here, looks like the 25th. So here's our 25th identity now. Alright, so that's the conclusion of part 6. Then we're going to get into our half angle formulas. Okay, in this next section, we're going to be proving our half angle formulas. Now, these identities here actually follow really nicely from our double angle identities that we just showed above. So I'm actually going to start here. I'm going to make a little note for you. This is definitely not something you would have to write on your paper, but we're going to use identity number 23. So you might want to make this note just in your notes, and then on your test, you obviously don't have to write that. Let's start with identity 23, which says that the cosine of 2 theta is equal to 1 minus 2 sine squared theta. So we're starting with something we already established. Now I want to isolate my sine squared theta. So what I'm going to do first is move that 2 sine squared theta to the left, move the cosine to 2 theta. So I have 2 sine squared theta equals 1 minus cosine 2 theta. So that's just an alternative form here. Then I'm going to divide by 2 to get 1 minus cosine 2 theta over 2. So I have sine squared theta equals 1 minus cosine 2 theta over 2. Now this is just an alternative form. Oops, let's box this in red. So we'll box this up here, and this is, I believe, our 26th identity now. So this is just an alternative form of one of our double angle formulas that we've already shown. Now what we're going to do is something specific. It's like a nice little technique here so that I can express the sine of 2 theta in terms of a half angle here. So I'm going to, on the side, I'm going to let x equal 2 theta. So this is very important here. If we let x equal 2 theta, now you don't have to show this, but then theta is equal to x over 2, right? That derives from here. So I'm going to make some substitutions into this 26th identity, and I'm going to write this as sine squared theta. I'm sorry, instead of sine squared theta, I'm going to write this as sine squared of x over 2, because I'm just substituting in theta as x over 2. So I have sine squared of x over 2 equals 1 minus, now the cosine of 2 theta, we know that 2 theta is equal to x, so that becomes, using substitution, 1 minus cosine of x over 2. Now I want to get sine all by itself, and this is actually how I end up with my half angle formula. So I square root both sides. Now if I square root the left-hand side, I have sine of x over 2 equals this positive or negative square root of 1 minus cosine of x over 2. So this is another unique identity here. This is my half angle formula, and this is identity number 27. Now we're going to show the next identity here side by side so that you can see how similar this is, but now we're going to use identity number 24. So I'm going to use identity number 24 here. So I start with the cosine of 2 theta is equal to 2 cosine squared theta minus 1. Now I want to isolate, just like I isolated the sine squared theta here, I want to isolate cosine squared theta so that I can express the cosine of eventually x over 2 here, a half angle. So I'm going to start by moving the 1 over, so I end up with 2 cosine squared theta equaling cosine 2 theta plus 1. Divide by 2, so I have cosine squared theta equals cosine 2 theta plus 1 over 2. I think in our textbook, though, we have that written as 1 plus cosine 2 theta, so I'm just going to switch the order here. So 1 plus cosine 2 theta over 2. You definitely don't have to do that. All right, that looks really similar to what we did on the left-hand side for identity 26. This is actually another equivalent form of our double angle formula, and I'm going to call that number 28. Now I'm going to use the same technique that we just used over here, so that's why I'm doing it side by side. I'm going to use this let x equal 2 theta. You need to make sure that you're writing that in your paper. That's actually going to be just a point just for doing this. So you get a point for saying let x equal 2 theta. So we use this idea now, and I replace theta for x over 2 here. So the cosine squared of theta becomes cosine squared of x over 2. So cosine squared of x over 2 is equal to 1 plus cosine of x over 2. Now solving for the cosine of x over 2, I square root here. So I have the cosine of x over 2 equals positive or negative square root of 1 plus cosine x over 2. So here are our half angle formulas. That's number 29. Okay, I just want to take a second real quick to recap something. I didn't do this in the very beginning. I probably should have when we got into our half angle formulas here. But the reason why these two half angle formulas that we've so far derived, the reason why they're important is because sometimes you might be given an angle here. Let's say it's alpha, and I want to know actually what the value of alpha over 2 is. Well, if I know what the value of alpha is, it makes it a lot easier to be able to calculate the value of alpha over 2 if I can just plug right into here this formula. So it is something that it will be useful, and we'll see that in our next section, 9.2. But also it allows us, when we know these formulas here, this half angle formula, we can transform an expression that has exponents into something that doesn't have exponents, but where your angles are just multiples of your original angle. So it is a helpful technique to be able to do this. Now I also want to talk about this whole positive or negative thing. Okay, so usually when you solve something, like let's say we have x squared equals 16, we get two unique solutions, right? X can equal either positive or negative 4. In this case, this is not trying to show that x, sine of x over 2 is equal to both positive or negative. This answer, it's only one. You have to actually pick one, and the reason why is because it's going to depend on where x over 2 lies. So whichever quadrant x over 2 lies, that's when you decide if it's the positive or negative value. So it's not both. So I just want to make that clear as well. All right, now the next thing that we're going to show is the tangent of x over 2. So I'm actually going to just start with writing the half angle here, tangent of x over 2. And I'm going to use what we just proved in 27 and 29 here. I'm going to set up the ratio of sine to cosine. So I have sine of x over 2 over the cosine of x over 2. I'm not really sure why I'm using the parentheses. I don't really need them, but I just did it. Okay, so let's just now use substitution. Well, I know that the sine of x over 2 is positive or negative square root of 1 minus cosine of x over 2 divided by positive or negative square root of 1 plus cosine x over 2. Now I'm going to rewrite this radical, okay, so that I can get rid of the fact that there are two radicals and make them just one radical here. So I have positive or negative square root of, I'm going to take the numerator here and divide it by this denominator, so I actually end up with 1 minus cosine x over 1 plus cosine x. So they end up, after I divide them, obviously the 2's cancel out because I'm multiplying by the reciprocal. Okay, now at this point, what I'm going to do is actually multiply by 1 plus cosine x over 1 plus cosine x. And the reason why I'm doing that is because I can create a perfect square in the denominator, and I can create a difference of squares in the numerator. So I'm going to multiply now by 1 plus cosine x over 1 plus cosine x. Okay, so I'm just multiplying the inside of this radical by this value. Now, I end up with positive or negative square root of 1 minus cosine squared x over, in the denominator, 1 plus cosine x squared, the quantity 1 plus cosine x squared. Now, this is actually extremely helpful for me, okay? The reason why it's extremely helpful is that I can rewrite the numerator here, 1 minus cosine squared x. Hopefully you're recognizing that as a manipulation of our identity cosine squared x plus sine squared x equals 1. So I can actually make a substitution here. So I have positive or negative square root of sine squared x over 1 plus cosine of x. I keep leaving off the x, sorry. Cosine of x, quantity squared. All right, now I just created basically something that I can take the square root of, right? So I see in the denominator, if I take the square root here of 1 plus cosine x, this I know has to be positive because our cosine of x is only between negative 1, right, that value here, and positive 1. So if I plug anything in, no matter what x is, it's going to fall between negative 1 and 1. So even if it's negative 1, then this is obviously all undefined. But I definitely, don't have to worry about this value being negative ever. Okay, so I don't have to worry about it being negative, which means I can now drop the radical here and just call that 1 plus cosine of x. Now in the numerator, we still have positive or negative sine squared x. Now, this is where we have some very crazy cases going on, so I need to explain this a little bit further in depth. All right, so we've got 4 unique cases that we need to look at. We're going to look at the values of x over 2 and x. So we're going to look at our half angle and our full angle x, and we're going to then take a look at the values of the tangent of x over 2 and the sine of x. The reason why we're doing that is because we want to compare the sines, okay, the sines of tangent to sine. Okay, so for example, we start with our first case. Now our half angle could lie in the first quadrant. If it lied in the first quadrant, our tangent of our half angle has to be positive, because we're comparing positive to positive, that ratio here. So our tangent must always be positive. Now x, if we double this angle measure, so we'll double this and we arrive at this inequality here. That means that x, again, you can see it even visually, if I have an angle measure here and I double that, well, it's going to lie either in the first or the second quadrant, depending on its angle size, the measure of its angle, but it's going to lie in quadrants 1 or 2. Now, if it lies in quadrants 1 or 2, if we look at the sign of that value, the sign of that would be positive as well, okay? Because our y-coordinates are both positive in quadrants 1 and 2. If we look at our second case, where we could possibly have an angle that lies in our second quadrant, that means then that the tangent is going to be negative, because we're comparing sine to cosine here, positive to negative, so we get a ratio that ends up being negative. Now, if we look at x, we double this inequality here, we arrive at this possibility. So here's the range for x. X can lie between pi and 2 pi. Pi and 2 pi is quadrants 3 and 4. So your full angle then lies between quadrants 3 and 4. 3 or 4, I should say. So if we look at this, the sign here is always going to be negative. Okay, it's going to be negative everywhere if it lies in quadrants 3 or 4. Third case. Let's say that our original half angle lies in the third quadrant. Now we have a tangent that's going to be positive because we're comparing negative and negative here again. So we get an overall positive value for a tangent. That means when we double this angle, so I double this inequality here, I arrive at this inequality. So now x lies between 2 pi and 3 pi. Well, 2 pi to 3 pi is actually quadrants 1 and 2. So it could lie in quadrant 1, it could lie in quadrant 2, and in which case the sign of your full angle, again, is going to be positive. Last up, we have our fourth case. If we have an angle measure that lies in the fourth quadrant, so we are looking at our half angle, it lies in the fourth quadrant, well then, our tangent, the sign of our tangent is going to be negative. Okay, the sign of our tangent will be negative. If we double that angle measure, we arrive at this inequality here that shows that the possible values for x. Now x can lie between 3 pi and 4 pi. Remember, this is 3 pi over here. 3 pi to 4 pi is either in quadrant 3 or quadrant 4. So your full angle can lie in quadrant 3 or quadrant 4, which means then you're looking at the sign here, the y values are going to be negative. So basically, what this is trying to show you is that the sign of tangent of x over 2 and the sign of x will always match, right? It doesn't matter what the value is, these signs will always match, which means then that when we bring it back here where we left off, the plus minus sign is going to drop here because the tangent of x over 2 always will have the same sign as the sine of x over 1 plus cosine of x. So this is actually our 30th, I think, identity right here. So the tangent of x over 2 is equal to sine of x over 1 plus cosine x. Now I'm sure you'll take away from this that the positive negative here just drops out, but the reason why, again, is those 4 cases. So just kind of gives you a little unique perspective here on why our identity looks the way it does. Okay, so that concludes now part 7, and we've got one more left, and that's the end of your Prove It notes.